Hello everyone, welcome back to our channel. Today we are going to discuss the giant pizza problem from the CSES problem set. If you love algorithms and problem solving, make sure you hit the subscribe button and check out the channel as I keep uploading the solutions to the problems. So without wasting time, let's get into the problem statement and see how we can solve the problem. So the problem is saying we are given with a family where we have n family members and m possible toppings, and each family member has two wishes whether the topping is good or topping is a bad. Okay, and we have to find a possible solution so that each for each family member at least one wish is fulfilled, and if we cannot find, print the impossible. Okay, so the problem statement is saying we are given with the options +1 -1 +3 and +4 -2. So we are saying these are the wishes of family members that they say about the toppings. So first family member say topping 1 and 2 are good. Second says topping 1 is not good, but topping 3 is good, topping 1 is not good. And third is saying topping 4 is good, but topping 2 is not good. And we have 5 toppings, and we have to decide that what could be the possible solution, like which topping to consider and which to not consider, so that each family member has at least one wish fulfilled. So if we consider these two options, and if I say let's consider topping 1 as to be considered, if I consider topping 1, and if we see these two options and say let's consider topping 4, and with this two, let's see, so we are considering topping 1, so we have to consider topping 3 for this problem for this person, and for this the wish is fulfilled, and we are considering topping 4, so this is fulfilled, and this is also fulfilled because we are considering the topping 3. And for 2 and 5 we have different options, so we could take any possible use case for them. So if we consider all the 5 toppings, then we are actually fulfilling the cases for both all the family members. This problem seems very easy, but is actually a NP complete problem, and it's a problem of 2SAT. We would be discussing this algorithm in detail in this problem, because we will be using this particular technique to solve this problem. So what exactly a 2SAT problem is? 2SAT problem is saying we have constraints which has two variables, and for each variable, like for each that constraint, we have two wishes, and at least one wish per person should be true. So let's suppose any person A has two wishes, wish 1 and wish 2. So for A to be true, we could say wish 1 or wish 2 should be true. I want you to pay attention to this particular thing, because this is a root of the 2SAT problem. So it is saying wish 1 or wish 2 should be true. So let's see how we can actually further analyze this thing. So if I say for A, W1 or W2 should be true, can I further break this thing into, if I say not of W1, if I'm not considering W1, then I should consider W2, and not of W2, I'm considering not of W2, then this implies that I should take W1. So this OR clause can be done to this particular thing. Now let's understand this. If I'm saying wish 1 or wish 2, any could be true. And if I'm saying I'm not taking wish 1, not of wish 1, then it implies that I should take, that I'm considering wish 2 as to be true. And if I'm saying I'm not taking wish 2, then this implies wish 1 should be there. So AND condition of both of this would be giving me this particular OR clause, which is setting this to be true, because both conditions to be true. And we now let's see how we can further deduce this from the test case, like from the we have like the options we are given. So if I say plus 1 or plus 2, so this actually literal meaning is including topping 1 or topping 2. So if I do not like not of plus 1, then must consider topping 2, and if like not of plus 2, then must consider topping. So if I reduce the expression of not of plus 1 to 2 plus 2, which is equal to minus 1 2 plus 2, and for second expression is not of plus 2 to plus 1, it is to minus 2 to plus 1. Okay. So now we have understood what are we thinking, in which direction we are going. So let's suppose, now let's see how we can actually make a graph from this. So let's suppose that I have two wishes, W1 and W2, and I have two literals, plus and minus. So I would be using a encoding for this, encoding for positive literals. For positive literals, I would be using 2 into I minus 1, and for all negative literals, it would be twice of I minus 1 plus 1. This is the encoding that we are considering. Okay. So for person 1 and person 2, it would actually be something like 0 or 2. For minus 1 plus 3, like for second person, it would be 1 or 4, and for plus 4 minus 2, it would be something like 6 or 3. Let's see how we can actually make the graph for this. So the graph would be something like the edges we would be considering is plus 1 to plus 2, then 3 to 0, according to that equation that we have deduced here, that is this equation. And for 0 to 4 and 5 to 1, and for this it would be 7 to 3 and 2 to 6. So this is how our graph would be, and then we would be finding the strongly connected component for this, and we would say if x and not of x lie in the same SCC, then it's an impossible case, because because this is a simple scenario, as if I could reach from 1 to negation of 1, because it would be giving me a contradictory equation, because I cannot have 1 and a negation of 1 in the same SCC, in the same strongly connected components. You will get a better picture while looking at the code. So let's see, let me give you the understanding of the code. So we have taken the number of family members and the M is the number of toppings, and we have defined the adjacency list for twice of the state because we are using a double encoding. So so we have taken string input of toppings and reduced it to zero based indexing, and then for positive literal we are using twice, and for negative it's twice of I plus 1. And then we are actually pushing this into the graph. So toppings once or one would be actually negation of topping 1, push back topping 2, and same for this. And transpose graph is we are using this for the SCC. Then we are finding the strongly connected components using the DFS, and then we are checking if the strongly connected component is actually existing. Like we are giving the which each element, each node belongs to which strongly connected component, and then we are checking if two components like I and negation of I, does it lie on the same component. If yes, then it's an impossible case and will return. If no, then we are saying if I is twice of I is greater than twice of I plus 1, then that's a true, then we can consider that topping. And if less than, then we are not considering that topping. And this is how our final answer would look like. Now let's run this case. So our expected output is we could consider all these 5 toppings, and now let's try to submit this code. Okay, so cp main.cpp, let's upload and try to submit this problem. Yeah, so it's get accepted. I know the solution could be quite tricky because it's a very new algorithm and actually NP complete. And I would recommend you to read the two-set problem once as well. And if you have any questions or any doubts, feel free to comment me in the chat or in the comment section. I would be resolving your doubts there as well. And this is a good question, I would say, because this is a real life problem, as we can see, and two-set problem is giving us the choices that whether to consider a particular wish, like considering the wishes of the person and how we are actually optimizing them to get the answer. So yeah, so this is the solution, and would be posting then another great solution for another problem. And let me know in the comments what another problem solution you want me to put on. So thank you everyone, and we'll see you in the next video.